protocol, and then we can begin.
Yeah.
So, and this is our NLP ML group, mainly students, research engineers, researchers, and so on.
Okay.
So when I told them, of course, about you, but let me do the protocol. Okay. So it is indeed a great pleasure for me to introduce Professor Partha Talukdar, who is with the faculty of IISc Bangalore Center for Data Sciences. And he is also a Google research scientist. Partha obtained his PhD from University of Pennsylvania, which is considered one of the cradles of natural language processing. And then he did his postdoc in Carnegie Mellon University, working with one of the gurus of machine learning, Professor Tom Mitchell. And that is when he was instrumental in creating the system called never-ending learning, which is famous all over the world. We, in our group also, we have used concepts and tools in never-ending learning. Partha received Google's Focused Research Award and Accenture Open Innovation Award. He is also co-author of the book on graph-based semi-supervised learning published by Morgan Claypool. Partha is one of the creators of Moodle, which is extensively used for NLP tasks dealing with Indian languages. So this is a great contribution to Indian language, natural language processing. Partha's research experience, extensive research experience, is in natural language processing, machine learning, knowledge graphs. And his recent research is focused on multilingual learning, learning in low resource setting, graph-based learning, automatic knowledge harvesting from web-scale datasets, and temporal information processing. We have a joint research work with Partha on some kind of pan-Indian morphology processing through deep learning systems and transfer learning. Partha leads an NLP group in Google Research India, focusing on significantly advancing the state of NLP in low resource setting, especially focused on democratizing information access for Indian language users. So this is a great contribution which will advance the state of art in Indian language NLP. He also founded Kenom to help enterprises make sense of the dark, unstructured data using knowledge graphs. Partha is indeed a very, very accomplished person with a lot of insight and a lot of experience on NLP, machine learning, AI, and it is, of course, a great pleasure to have Partha speak to our group. Thank you, Partha.
Thanks, Pushpak, for a very generous introduction. So just when I was trying to share my screen, it's asking me to give some permission for which I need to quit WebEx and join again. So my apologies. So I'll just quit quickly and then join back again. Yeah, so that I can share my screen.
Okay, please do.
Yeah. Yeah. Pushpak, are you able to see the screen now?
Yes, yes, I can see it. Yes.
Okay, let it come up. Yeah. Okay, so I guess finally we are there, and my most sincere apologies for all of this delay. Yeah, just kind of like, especially on a Saturday when you guys are all giving me this time. Yeah, so my sincere apologies. So thanks, Pushpak, again for giving me this opportunity to speak to your class. It's always a pleasure. And thanks for a very generous introduction. I don't know whether I deserve most of that. So in today's talk, I want to give you like a high-level overview about knowledge graphs. Again, that area has like grown over time, and I'll not be able to like cover all of it. But then knowledge graph is an important area, and then like we know that deep learning is like is like a very popular topic these days. So I wanted to kind of like talk about the intersection between knowledge graph and deep learning, and like I said, highlight some of the work that we have been doing over the years at this intersection. And at any time, if you have any questions, please feel free to stop me. I prefer it to be an interactive session rather than one way. Okay, so the thesis behind this line of thinking, right? And then why we should say care about knowledge graphs in the first place is to kind of like suggest that knowledge and background knowledge which we may store in the form of say knowledge graph or some other structures is important for AI and machine learning, and ultimately for intelligent decision making. So one example that I use to drive home this point is, let's say that like you don't have time to read the daily newspaper, and then you want a system like which reads the daily news and summarizes it for you. And such a system came across a sentence like State Farm stocks tumble along with Berkshire Hathaway. So in order to make sense of this particular sentence, we need lots of external knowledge, right? Let alone for machines, even for us as humans. We need to know that there is a concept called company whose two instances are mentioned here. Something called instances are State Farm and Berkshire Hathaway. There is something called a stock market where these company stocks are traded. There are price associated with them, and then there is volatility. So none of those external knowledge, which is important to make sense of this particular sentence, is mentioned in the sentence itself, right? And that's by design of language, because we use language for communication, and we have some common understanding, and we want to speak the delta with respect to that common shared knowledge that we have, right? Because we want the communication to be informative and also efficient, right? So in order to convey something, if I have to give you this whole background of what is company, what is stock market and all of that, so that's not going to be a very efficient communication, because in order to maybe even convey one concept, we'll need 1 day, right? So so yeah, that also gets reflected in say when we are writing this data or typing it out. But of course, machines don't have that context, right? So the question is how we can provide machines with that context. Now, even if I had all of that external knowledge that I say swapped in, even as a human, why there might be a correlation between the stock prices of these two companies, that may still not be very clear, right? But if I showed you something like, say, Berkshire Hathaway is mentioned here, they have a subsidiary called Heinz. So you may have seen those ketchup bottles, which is insured by State Farm, which is also mentioned in this sentence, right? So one plausible way why there might be correlations between the stock prices of these two companies could be that something bad happened to Berkshire's subsidiary Heinz, say, right? And that the losses of Heinz are going to get passed on to their insuring company, which is State Farm. So State Farm's outlooks also don't look good. So that needs to be priced in, and that gets reflected in their stock price, right? So hopefully our interpretation of this particular sentence is much deeper now compared to, say, like 1 minute before, when we didn't have this background knowledge to aid our interpretation and analysis of this sentence, right? So hopefully you will agree with me on that. And this this background, the structured graph that we are utilizing now, it is called a knowledge graph, or which is a fragment of a much larger graph, which we call as the knowledge graph, where nodes represent entities or objects of interest, and the edges represent the relationships connecting those entities, right? So that's the basic idea, and maybe provides you some motivation of why we should care about knowledge graphs, and how, at least at a conceptual level, how they could assist in our analysis of real world data. Okay. Okay, so the thesis here is that deep learning augmented with knowledge graphs improves performance. And then in terms of inequalities, it's deep learning plus knowledge graph is better than deep learning on its own. Okay, so what I talked just now is the factual knowledge graph, where we have entities and relationships. And here we are wanting to go towards things and not strings. Okay. Then there are other types of knowledge structures. So kind of thinking of more broadly, not just knowledge graphs, but other types of knowledge, but which is represent in the form of a graph. For one example of that will be, say, syntactic graph, say dependency or parse tree structure in a sentence, where the nodes are words and the typed edges are the dependency relationships amongst a pairs of words. Similarly, you can also have temporal graphs, where, say, the nodes could be events or time expressions, and then the edges represent relationships among those temporal events or time expressions, like, say, before, after, and all of that. So while my focus will be a lot on factual knowledge graphs, but I'll also utilize these other types of knowledge structures, if you may call it, and broadly think of these as multi-relational graphs. Multi-relational because my edges have different types associated with them. So there are different colors on these edges. So how I can utilize all of them for deep learning. So broadly, for today's talk, knowledge graphs are going to be, say, multi-relational graph, where if you have developed methods for multi-relational graphs, then maybe you can apply them across these different methods. So the talk I have divided into 3 parts to give you a overview of the life cycle, maybe, or at least one type of life cycle around knowledge graphs, where, say, if you have unstructured data, right? So how do you go from that unstructured data to some form of structured knowledge? So that's the part 1, building the knowledge graph. Second one is, when you have this kind of a symbolic representation, how do you make them amenable to be utilized in, say, deep learning methods? And so that's where doing some sort of embeddings of these graphs will come in. So basically, how do you go from graphs to vector representations of various elements that are there in the graph? The third part will be how I can use these kind of embedded knowledge graphs into some downstream task. So here I'm going to run you through one example of say word sense disambiguation that we worked on. And the hope is that once you have developed your deep learning methods, now you can do the reading of this unstructured data better. And then there is a virtuous cycle that could kind of go on and on. So that's roughly the plan for today. So before we go into the first part, and again, I'll not be, since we have limited time, we will not be able to go into the depth of all of these things, but I'll give you some flavors and pointers that you can follow up afterwards if you are interested. Before I proceed further, any questions so far? So I guess not. So I'll move on. Okay, so on the KG construction side, so the need for knowledge in AI has been recognized for a while, but the challenge has been how do you build this kind of knowledge structures over time? And there have been over time multiple efforts have been attempted, ranging from say building efforts like say Sitecorp or Freebase, all the way to more somewhat recent efforts like say NEL, that Pushpak was also talking about. But you can think of these as a spectrum. So where Sitecorp and Freebase, where all user contributed, so everything was typed by humans. So that's high precision, but how do you scale those to large amounts of large coverage? That becomes a problem. But then when you have these machine learning driven approaches, they tend to be on the low supervision, so you can scale them up, but the quality maybe in all parts may not be as good as the human curated efforts. So the point here is that there have been multiple attempts in building these kind of knowledge graphs with different types of design considerations. Okay, all right. So here is a attempt at building such a knowledge graph by a system called NEL, which stands for Never Ending Language Learning, where I was also part of. And what you see in front of you is a fragment of a knowledge graph that NEL learned by reading web documents over a 10-year period, right? So that system was iteratively running over pretty much a decade, and then it's able to learn things like Toronto Maple Leafs is a entity which is a hockey team. Their hometown is Toronto. They play hockey, and then they won Stanley Cup, right? So all of these things are being read from being read and extracted and organized by reading web documents on a continuous basis over a decade period. Right? If you are interested, you can go and browse these URLs, rtw.ml.cmu.edu, and then you can browse the whole knowledge graph that's there. So, talking about say how NEL works, that's going to be a talk in itself. So I'm not going to get into the details of that, but I just want to leave you with one key idea that enabled NEL to reach as far as it did, and that's the idea of semi-supervised bootstrap learning, right? And what are the challenges with that? So let's say you are interested in acquiring the concept of cities, right? So basically you want NEL to learn a lot about cities. So what you do, so you want to start in a semi-supervised or weakly supervised setting, because you cannot provide lots and lots of label examples of just say cities, because cities is not the only thing you are interested in, although we are talking about that as an example now, but you are interested in tens and thousands of different types of concepts that you want, say, NEL to know about, but you cannot provide label data for each and every one of them, right? So if you have unlabeled, lots of unlabeled data and a few seed examples of, say, cities like, say, Paris, Pittsburgh, Seattle, and Montpellier, then what you do is basically one idea of bootstrap learning is you go and check what kind of, in what contexts these kind of seed entities are present. For example, mayor of, say, Paris, or live in Paris, or live in Pittsburgh, all of that. And then once you have induced these kind of patterns, you go back and extract these entities again from text. But the problem is that while you may get additional city names by applying these kind of templates, but you also going to get some sort of noisy extractions. For example, if you get live in Pittsburgh and live in denial are both likely to be found in corpus. So now you find like, denial becomes basically your seed for the next round. And then when you go and induce patterns from the corpora, now you start getting into like, psychological attributes and like, the whole thing goes off way, right? So you started off with cities, but now you're ending up with anxiety, selfishness, London, like, mix of these kind of psychological traits and cities, which is not desirable, right? So people had used these kind of bootstrap learning ideas before, but this problem of semantic drift, that you start from cities and you end up somewhere else, was a big limitation. So the main key point here is that while doing this kind of learning in a weekly labeled setting, the problem is under constraint, right? So we are not able to put enough restrictions on what the model learns. So that's where one key idea of NEL comes in, is to do coupled semi-supervised training, right? So what we discussed just now is this, that if I am just doing this problem in isolation, that like a noun phrase, deciding whether a particular noun phrase is a person or a city, that's a much harder problem because that's under constraint, right? But if I learn multiple of these semi-supervised learning problems together and enforce some sort of coupling constraints among them, then it's going to like, those are going to constrain each other, and it will hopefully prevent like, semantic drift. For example, if I have like, say, a noun phrase person, a noun phrase, and I'm trying to decide like, whether it's an athlete, person, sports, team, coach, and all of that. So what these arrows, the green arrows, are saying is that if I am classifying this noun phrase to these two categories, then they can be compatible with each other, right? Because an athlete is going to be a person, but if this noun phrase is a person, then it cannot be a sport, right? Because there is like a type inconsistency between them. And then if that noun phrase is a sport, that it cannot be team, right? So as you see, that rather than making this kind of decisions in isolation, we are now kind of like, making multiple decisions and enforcing some sort of constraints among them, so that like, this kind of like the semantic drift that I was talking about earlier doesn't happen, right? And you can do this both at an individual noun phrase level, but you could also do it on a pairwise noun phrases and enforcing relationships among them, right? For example, if you say that like Pittsburgh is a city, then it better be the case that Pittsburgh also has a mayor, right? Because like, say, a sports team or a psychological trait is not going to have a mayor, or is going to have like, police chief or something like that, right? So that's kind of like a key idea of doing this kind of coupled semi-supervised learning, right? Now there are a few other key ideas that like, okay, that if these kind of like, constraints are important, then how do we like, go and learn these kind of constraints automatically from data, rather than like, humans have to manually provide those kind of constraints. So we had a paper, a summary paper in CSEM 2018, where we summarized basically like, lessons learned and opportunities. So if you're interested in this area, I encourage you to go and take a look at it. We also had a tutorial in ICML 2019 and in KDD 2018 on how to build like, the internals of NEL and how it works and all. So the videos and the slides for all of those are available at these links. So I encourage you to go and take a look at that, right? So so this is about NEL and an effort towards like, building these kind of knowledge graphs from unstructured data. Okay, so Sapan, I don't see all the questions clearly, but what is the associated ontology for NEL? Is it updated as per learning goes? Yes, Sapan. So what happened was you provide some sort of initial ontology for NEL, and then NEL kind of like goes and finds additional instances for those ontology, which are like these categories and relationships. But it also had the capability to induce new categories and new basically extend that ontology further. For example, it learned at some point a lot about rivers, and it not lot about cities, right? So like, what are the river names, what are the city names, in what kind of context people talk about rivers and cities. But then it saw that like, people also mention in text rivers and cities in close proximity with like, more than random chance. So given that cue, it basically went and discovered that there should be like a relationship between these two categories, and then came up with a new relation called river flows through city, right? So that becomes a new learning task for NEL, right? And that by doing this kind of coupling with these other constraints that I was talking about, now that becomes a new problem, and it will like, go and find new instances of that particular category and relation. So yes, yeah. So it had some human specified initial ontology, which you could also like add over time. But then it also had its own ability to add new relations and categories. So yeah, great question. Any other questions so far? Okay, I'll move on then.
Sir, I have one doubt.
Yes, please.
While manually creating these constraints, let's say one noun phrase was earlier there, but that has been modified by like the modified use of that noun phrase has different meanings that creates confusion. Let's say we are combining like relating one noun phrase with player or person, something like that, but using that noun phrase, one new team has evolved. The team name is also a noun, that same noun phrase.
Yeah.
But in a graph, we should not have a edge from a player to team, something like that. But now we will have to have one edge. That creates confusion because of the evolved use of same noun phrase in different ways by different people.
Right.
How do we handle those cases?
Yeah, that's a great point. So I haven't kind of like talked about all of the details here, but in NEL, a same noun phrase could connect to different concepts, right? So for example, if you take the noun phrase, say apple, right? That could mean like fruit the apple, or it could mean apple the company, right? So you have these kind of like, say, entities, and those entities, each entity could get expressed in text using many different noun phrases, and the same noun phrase, like just based on the identity, could refer to different entities based on different contexts that in which it occurs, right? And then the coupling constraints that I was talking about, you basically enforce them over those entity space, right? Rather than just kind of like starting from the noun phrases. So intermediate abstraction in terms of entities and concepts. And then you apply basically these kind of like coupling constraints on top of those abstract entities and their types and relations.
So
And
those constraints, sir, just one more doubt in terms. So those constraints we have to add in like manually, or model will learn over the
so that's
time?
the key idea too that I'm not talking about today, where so some constraints are very easy to infer. For example, if you are specifying the relation, right, say mayor of city, so you know that the mayor of city, like the source is a person and target is a city, say, right? So those kind of like type-based constraints you can automatically infer from the type signature of the relation itself. But there are also other capabilities where you could derive these horn clause based constraints. For example, if you have things like Virat Kohli plays for Team India and Team India plays sport cricket, then Virat Kohli should play sport cricket, right, and not hockey, say, right? So those kind of like by doing analysis of the induced graph, NEL also had the capability to discover new types of additional coupling constraints. So yeah, so the constraints are also automatically expanded.
Sir, again, just to clarify, whether NEL is able to identify new categories or more specifically new classes of entities and relations. For example, new classes means player is a class, person is a class, company is a class, right? So
Right.
whether the NEL is able to identify these new classes for both entities and relations, and not just instances of classes. Means I am aware that we can find out instances of a class, that class should be already existing in our ontology. But
Yeah.
I'm not aware that whether NEL is able to find out new classes or new categories itself.
Right. So that's what I was saying in the river flows through city example, where it discovers new relations on its own, right? So you can think of this as like a curriculum building, right? So where you know about like, the unary, say predicates, like say cities, because they're just taking one argument, right? So it kind of like first build competencies in learning about those unary predicates, which are these categories. And then once it had some sort of competencies of that kind, then it kind of like, automatically inferred this binary predicate, which is a relation, which is a river flows through city, or musician plays musical instrument, right? So those new relation types are automatically discovered. For category discovery, there was, so the relation discovery and what happens after that, those were part of the life system. For the category discovery, it was, there was like research work that was done, but it was not part of the life system.
So as you said that a new relation, that is river flows to city, is discovered. But
Yeah.
in order to discover this new relation, was
Right.
river and city, these two entities already present in the ontology?
That's right.
They
Yes.
weren't present.
They were present, right? That's where the notion of curriculum comes in, right? That like, in order to form a word, you need to know what the characters are, right? And then in order to form a sentence, you need to know what the words are, right? So you kind of like go from lower complexity to higher complexity. So those lower complexity things, like say, which are like say these categories, those were already present, but now combining and composing them, forming the higher level relationship is what NEL did.
Okay. So any clues that how we can find out these categories, like for example, river and city? And as you said that they were already present in the ontology, right? But how we can find out these new categories, like river and city?
Yeah.
You just
Right.
said about the relation category, which is found out, but how
Yeah.
to find out the actual new concepts which ontology doesn't has?
Right. So again, there like there are like multiple approaches to do that kind of thing. So ultimately, it's going to become, or like a dominant way to approach this is like some sort of like clustering, some grouping, right? So if you're starting with the noun phrases, then you can like end up with some grouping of those. So we have also done some work on like tensor factorization based approaches to do these kind of like groupings better. I'll be happy to point you to some papers in that direction.
Okay, so thank you so much.
Sure. I think there are other questions. So Tejpal Singh asks, how do knowledge graphs deal with obsolete data? Yeah, that's a great question. So like, we live in an evolving world. So where like, most facts become obsolete. So one way to do that is to delete those facts, but that's going to be suboptimal because you did all of that work. And then like, and some of those old facts also may become useful in the future. So one way to handle is that you assign some sort of time scopes or time stamps to those facts. So let's say like an edge is there, say Barack Obama, president of USA, then you say that he was president, or that particular fact was valid from 2009 to 2016, right? So that way, like, during which period that was true, And then if you are querying it afterwards, then you can decide how to utilize that. So that's one way to handle obsolete data.
Got it. Thank you, sir.
Yeah. Sandeep has a question. In the example of semi-supervised setting, denial is being misclassified as capital, leading to wrong results. Okay, so even before inserting denial into the city bucket, can't we have a verification or background check with some boardnet, etc., and then add it to this city? Yeah. So Sandeep, if you have external resources, you could always utilize it. But it's also a question of what's the coverage of that external knowledge, and whether that and how accurate that is also. So yeah, so if you have additional resources, you could absolutely use it. But having a broad coverage knowledge source is a problem, and that's why we are looking at building these kind of resources. If lots of broad coverage resources covering different domains and their factual knowledge were there, then we would not even have the need to build or pursue this kind of research. But yeah, but for a particular domain, if you have good resources, you can definitely utilize that. Not just for verification, I would say, why don't you just seed the whole model with those external data, right? So now you can collectively build a bigger knowledge sources. So Sandeep asks, as you mentioned, KGs will be created continuously. They should be updated continuously. How do we update the existing relations in case of a conflict? Yeah. So Sandeep, in case of NEL, there were multiple evidences that were used. Some of them would be for the same one predicate or one category or one relation, 10 different algorithms will be doing the same thing with different biases and different competencies. So one way to look at is how much of redundant evidence that I have, how many of those components are pitching for this particular fact. So that could be one way. The other will be how much of evidence you have seen, say how many sources, how many pages you have seen that particular fact being mentioned. You could also look at this kind of constraint-based reasoning that I mentioned, that okay, I have this particular fact, does it gel well with other things that I know? So based on those kind of multiple evidences, you could make a decision whether to include it or not. Does NEL have probability assigned to the triplets? Yeah, so there is scores associated with each one of the facts. Okay, so great questions, everyone.
So Partha, Kaveri has a question.
Okay, yeah, Kaveri.
Couple
Oh yeah, Kaveri, yeah. Yeah, a couple semi-supervised training finds the relations between two different noun phrases. Can it be used to find the relations present in single noun phrase? So Kaveri, when you mention relations present in single noun phrase, are you talking about unary attributes, or because when you have say relations at least at the binary level, then it will be another noun phrase. Yeah.
Yeah, okay. Can I give one example? Like
Please,
noun
please.
phrase, there would be a noun phrase like when I say like a finger of left hand, and
Okay.
we can say same thing like a left hand finger. So when we say left hand finger, this becomes one noun phrase. So now there are two different entities, left hand and finger. So and there should be some relation exists between that, like a finger is a part of left hand.
Right.
So so we talked about the semi-supervised training. So it is able to find the relation between two different noun phrases. But can we use to find the relation between the single phrases if two entities are present in single phrase?
So she means compound nouns actually.
Compound nouns, yeah. So kind of how do you parse even say noun phrases, right? Yeah, so I mean, it depends on kind of where you are defining those your definition and scope of your noun phrases, right? So if you are kind of starting with say fingers and hand, that compound noun phrase, you're going to find those two parts, and maybe and then if you have a part of relationship, right? Which is kind of seeded with say other types of part of relationship. For example, tire is part of say car, or finger is part of leg. So based on those kind of like, distributional analysis and how those things are present in in corpus, you could maybe kind of like, also infer here that like, the finger is part of left hand. Now, I should point out that Nell had kind of like looked at two types of information while deciding whether a for this is for classification of a single noun phrase, not necessarily trying to infer types or like relationships among different components. So there it looked at kind of like inside the noun phrase, what kind of attributes are or signals are present, and then also looking into the context. For example, if you have like say Indian noun phrases ending in pur, right? Or like say Western or English noun phrases ending in berg, then those are likely to be say location. So those are kind of like more looking at morphological signatures, like some suffix related information, but doing that all of that automatically. And then like the context will be like say live in, whatever comes after that is likely to be a city. So looking at, so since you are talking about looking inside the noun phrase, so there were some components within the NEL system which looked inside the noun phrase to derive features from them to classify to different categories that noun phrase could belong to.
Okay, thank you, sir.
Okay, does it have, Sapan has a question, does it have attribute relations like population of a country, attributive relationship? Yeah, so I mean, that's an interesting question. So it's a issue of like, how do you represent the value of an attribute, right? So, so like, whether you want to create that as a node or just kind of like, store the value as just like a value as property of a node. So yeah, it did have like, this kind of like attributive relationship, but to a large extent, I would say like, the two endpoints were like, mostly like entities. But I think there were some relations or some attributes where the endpoint was a value and not an entity on its own. Okay, great questions, everyone. So if there are no more, then we can maybe move on. Okay, so there are two types of knowledge or like a knowledge graphs you can think of. One is the ontological knowledge graph, right? So which is what I've been talking about, say like NEL, where you have like an underlying schema, and then you're populating the knowledge instances with respect to that, right? But then, and like, these are nice because these are kind of like, well curated, but building them could require supervision. All the systems like NEL was trying to cut down on that supervision need by utilizing these kind of coupled semi-supervised learning type of ideas. And on the other spectrum, you have open knowledge graph, which are ontology free, right? So like Mossam and his group at IIT Delhi and formerly at University of Washington has done lots of work in the area of open knowledge graph. So where your entities, so in this case, these entities, even though I'm putting them some string here, but you can think of those as like, canonicalized strings, right? But in case of like open knowledge graph, nothing is canonicalized, nothing is normalized, right? So you're just representing everything that in the surface form that you find them in the corpora. So like Obama and USA are two nodes. So these are all at the noun phrase level, and this ontological is at the entity level. So here you have the relation, say, was president of, yeah, so now these are kind of like easy to build. These are high recall, but they end up with fragmentation, right? So now say Obama is one node and President Obama is going to be another node. And then the question is, how do you kind of like, reconcile those? Because you don't want to have like a fractured view of the world where the same entity is getting split in multiple different nodes. Okay, so we have, I guess, about 20 minutes or so. So Pushpak, how are we doing?
Partha, we can go on.
Okay.
20
All right.
plus 20 plus 15 is fine.
Okay. All right. Yeah. So I'll try to. Yeah. Okay. So one method, so how to do these kind of say extractions for the ontological case. So again, in a lightly supervised setting, is the idea of a distantly supervised relation extraction, right? So relation extraction is basically the problem of, like, say, when you're given Obama was elected as the president of USA yesterday, you want to infer that precedent of relationship exists between Obama and USA, between these two noun phrases. And maybe you can do some resolution of these noun phrases also. So in order to do this kind of relation extraction, you can take like a supervised approach where you go and label instances in sentence and then do these kind of extractions. And the other is going to be distantly supervised, where the question is whether we can do the same task but in a lightly supervised manner, because if I have to go and label individual sentences, then it's going to be very expensive. This is like post-NEL work that I'm talking about. So this was not part of NEL as such. Yeah, but we did some work on kind of like Indian NEL, focused on Indian entities and relationships. So there some of these ideas were used. So the idea of distantly supervised relation extraction is to pose this as a multi-instance, multi-labeling problem. So where you have for each entity pair, say Narendra Modi and India, and you have the relationship called like say Prime Minister of, right? So what you do is you go and find out sentences which mentions these two noun phrases, Narendra Modi and India. So basically for each one of these sentences, you're going to find presence of both of these two entities or noun phrases, right? Now what you do is you make this assumption, and let's say this is our seed instance, right? So one of the examples that I gave of this Prime Minister of relationship is Narendra Modi, India. Another would be, let's say, Boris Johnson and United Kingdom, right? So so what we do is we basically create this kind of like instance set comprising of all of these sentences. And now we basically assign this label not to individual sentences or individual instances, but over the whole bag, right? So we call this as the instance bag or instance set, and the label gets assigned to the bag, and then saying that in this bag, there is at least one sentence which expresses this relationship between these two entities. So each bag corresponds to one entity pair, okay? So now, as you can imagine, assigning this label to a bag is an easier problem compared to, say, going and labeling each and every one of those instances, right? And this is called multi-instance learning, as opposed to the standard single instance learning in machine learning, where for each instance, which would be like a sentence in this particular case, you assign a label, but that requires far more judgment from the human time perspective, which is not available abundantly. Okay, so hope this idea of multi-instance learning is clear. And then we basically have a method called reside, so which is like a relation extraction using side information. So I'll not go into the details of too much of these things, but here the point is that if I have like a sentence, then by stacking multiple deep learning components, including something called graph convolution networks, we can basically create a representation of the whole bag of instances, which corresponds to a single entity pair, right? And then for that single entity pair, I know what relationship exists between them during training time. And then based on that prediction over the bag, if I suffer a loss, if I make an error, I basically do back propagation to learn, basically to update the parameters of this particular model. So the key idea here is that this is a deep learning model but we are using some kinds of side information to make this classification better. And then, like, by doing evaluations on benchmark data sets, which was available at that particular point of time, we find that the reside method, which is this red line in both curves, is outperforming other methods, other distantly supervised methods. So so this is precision recall. So higher on both dimensions is better. So Sandeep has a question. All relations in KGs need not be equally important, right? So do we have a ranking of the relationships of entities? So all relationships, I mean, it's a kind of like a task specific question, Sandeep, right? Because who decides which relations are important and which ones are not, right? I mean, if some relationships are not important, then maybe you should not be including them in the KG at all, unless they have some derivative benefit that, like, they provide some good coupling constraints for, like, other important relations to be learned well. So yeah, so I think it's a kind of like task specific issue, but here we are trying to build like a general purpose knowledge source which could be, like, useful for many different downstream tasks.
Yes, sir. So the question is in regards to summary generation.
Okay.
So in that, you might not need all the relations to summarize a particular concept, right? So in that case,
absolutely. Yes, yeah. So yeah, I mean, like, I mean, the knowledge graph is going to have hopefully, like, a lot more information than what you care about, right? So
yes.
yeah, so if you're trying to do summary, like, for the longer document that you're trying to summarize, maybe you will need a mechanism to select the relevant parts from the knowledge graph, right? That's kind of like, getting expressed in the document, and then maybe, like, utilize that subpart to do your summary better.
Yes.
Yeah.
So if we are already creating a knowledge base, and if we kind of include this information also, like which relations are important or which relations have a higher relevance, then that could be directly used rather than creating another knowledge graph for purpose.
So
Right?
I'm saying that as like build a general purpose knowledge graph, right? And then do selection from that in a task and instance specific manner during runtime, rather than building like a whole separate knowledge graph, right? Because the whole point is to kind of like give back to the same common source, because once you kind of like, fragment, and then if you're updating those fragments, how does it kind of like, go back to that original knowledge source, right? So build a general graph and then do selection in a task and instance specific manner.
Okay, sir.
Okay, so Sapan has one question. The side information of knowledge graph embeddings are pre-trained and fixed, or updated and learned jointly. The embeddings are learned. So I'll talk about embeddings later on if we get to it, but those are learned jointly at the whole graph level. So Ankush has a question, how NEL works when synonym entities or relations are encountered. How is it inserted into KG? Yeah, so that's where, like, before inserting into the KG, multiple evidences are used. Like I was saying, like, multiple components that may have vetted towards inclusion of a particular inference into the KG, or in how many sources you found that particular fact to be present. And then how does that particular new fact gel well with other facts that you know? So, like, multiple criteria were used together. Okay, so that brings us to the first end of the first part of the talk, which is looking at building the knowledge graph, right? The second part I want to talk about is how we can build embeddings of these graphs. So kind of, here there are two views. One is the symbolic structural knowledge graph that we have been talking about so far, which are these multi-relational graphs with different types of nodes and relationships. And then with the emergence of deep learning and representation learning, we can also think of like, embedding these graphs and its components in some sort of continuous space. For example, GM and Toyota and competes with our nodes and relationships in this graph, but I can maybe also equivalently represent them as points in some high dimensional space that I have projected in 2 dimensions for easier readability, right? So GM is a node here, Toyota is here, and competes with is a relationship connecting them. So we think of this as basically a spectrum, right? So where you have this kind of like symbolic graph at one end, then continuous embeddings at the other end, and how we can go back and forth between these 2 types of representation, right? So, so today I will be primarily talking about this direction. So if you have like the graph, then how do you learn embeddings of that particular graph, which is the topic of a very this is like of a popular topic of research called knowledge graph embedding, which has seen a surge of work over the last couple of years. So what is the key idea here? So the key idea is that I have these kind of triples in my knowledge graph, say HRT, Barack Obama, President of USA, and then I want to learn embeddings for each one of these things, right? And then how do you represent these different entities and relationships? That's also a question. But for now, to keep things simple, let's assume that we have vector representations for all of them. Okay. So there are varieties of methods. So in case of this, one of the earlier methods called TRANSI, which stands for translational embeddings. So you basically have like vectors associated with H, R, and T, and then you say like H plus R should get me closer to T. Okay, so that's basically is the constraint that you want to enforce, that I want to learn H and R and T so that this particular type of constraint is satisfied among them when I learn the embeddings for them, right? So similarly for these other types of methods, you also have similar types of constraints, but all of them, if you abstract away, learns this kind of a scoring function. Okay, so which you can call as like triple scoring function. So F, H, and T with respect to R, and all of these methods basically vary in terms of what kind of scoring functions, triple scoring functions are used. Now, what you do is that from the knowledge graph, where you have only, like say, positive instances, you basically want to maximize the scores of those positive triples, okay? And then you want to minimize the score of the negative triples. The negative triples are not present explicitly in the knowledge graph. So that's also an open problem. How do you kind of sample negative, good negative instances from the knowledge graph? And one common heuristic that's used is just randomly sample edges, because if you just randomly sample some edge from the knowledge graph, it's not going to be present in the, it's not going to be like a true fact in the world, right? So yeah, so this is the positive and negative triple. So yeah, so Swaroop, this is kind of like related to skipgram, just in the sense of, I would say, the negative sampling. Maybe that's what you are referring to as well. But otherwise, there is no context here. So this is operating all over the graph and not over sentences, which is where skipgram style methods would operate. But yeah, but similarities are there in terms of the negative sampling approaches. Okay, so this is as I said, there is an explosion in the these kind of methods over the years, and all of them have this kind of a scoring function, and they differ in terms of what type of scoring functions are used for the training. So so we talked earlier about this problem of so yeah, so that was a very quick overview of say how graph embeddings work. So given a graph that you can embed entities and relation nodes and relations into some sort of vector space. Now let's look at the problem of canonicalization, which is also the problem that we discussed earlier, that multiple noun phrases could refer to, say, one concept, right? One entity. Say Barack Obama could get expressed using the strings Barack Obama or Mr. Obama, and then Mumbai could be, say, referred in text as Mumbai or Bombay, right? So how do we do this? The idea here is that, let's say I have two strings, Barack Obama and Mr. Obama, and I don't know whether they are related. Are they right now referring to the same entity or not? I don't know, right? But by doing some sort of open knowledge graph construction, like I was telling you before, where I didn't have a schema that I extracted with, so I see that both of these noun phrases are married to this single noun phrase called Michelle Obama, right? So maybe, marriage is not a very tight relationship nowadays. So the marriage relationships could change over time, but to a large extent, right? So if two noun phrases are married to a single noun phrase, then maybe those two noun phrases are likely to refer to the same entity. So it's basically, we exploit these kind of structures from an open knowledge graph to do this kind of canonicalization. So what happens is, given some unstructured document collection, we create this kind of open knowledge graph, and then we do embeddings of those open knowledge graph, and then for each noun phrase we get a point in space, and then we do some sort of clustering over those noun phrases in that learn phase post KG embedding to discover what kind of entities are there. And the hope is that these kind of clustered entities are all basically referring to the same, clustered noun phrases are referring to basically one entity. And then we also use side information to constrain this embedding learning phase more. For example, if you have an entity linking system, which is saying that okay, this Mr. Obama and Barack Obama point to the same node in my KG, so you should be bringing their embeddings closer together. So we basically enforce those kind of additional constraints. Someone also mentioned about utilizing other sources like WordNet, and that's exactly what we do here as well. So for example, two strings, if they're present in the same scene set, so maybe we should be bringing their embeddings closer together. So we enforce those kind of additional constraints during the embedding learning phase. And then we find that when you apply these kind of constraints, you do better. So that SESI is our method compared to just kind of utilizing these individual components. So what we find is that if you combine all of these signals and learn a representation jointly, then you are able to do significantly better discovery of these entities. Someone asked a question earlier about discovery of categories. So similar type of ideas could also be applied at a category discovery phase, but here this is at the entity discovery phase. So some interesting results that we were able to find is that so we were able to, so this is embeddings of these noun phrases that's learned by using this SESI kind of an approach. So we are able to find that GlaxoSmithKline, different spelling variations, and GSK, the model is able to bring their embeddings close by. Now, if you see GSK and GlaxoSmithKline on surface, if you say try to do edit distance, they would look very different from each other, right? But since we are using the structural context of the graph, maybe it's saying okay, GlaxoSmithKline has CEO X, and then GSK also has CEO X. So we are able to now utilize all of that jointly to bring these kind of noun phrases together. Similarly, we also were able to discover that Sakyamuni is another name for Gautam Buddha, right? So again, if you were thinking of using edit distance, those do look very different from each other, but now through this joint embedding learning approach, we are able to bring them closer together. Someone asked earlier about the problem of like obsolete data. So I said that we can enforce some sort of timeline, right, or some temporal annotations over these edges. So we have we had developed a method called HiT, which was one of the earlier methods of its kind of doing this kind of knowledge graph embedding, but in a temporally aware manner. So where we also take this time into account, and then we have some hyperplane based mechanism where each hyperplane corresponds to different time units. And then we basically, if a particular fact is true at a given time unit, we basically project their embeddings onto that particular hyperplane and then try to learn the KG embedding in that space. Now, since then, there have been like, multiple follow-up work by others and like, performances for these kind of time-aware based embeddings have like, improved. But even in those earlier works, we found that if you're learning these embeddings in a time-sensitive way, then you end up learning better embeddings compared to, like say, if you ignored time completely.
So I have a question regarding the embeddings.
Yeah.
So generally we use the embedding to represent the higher dimension space to a lower dimension space. But let's say our knowledge graph is very small, and we want to embed it. So when we give a higher dimension, so does it affect the learning, embedding learning, or does it affect the downstream application where we are using this embeddings?
Yeah, I mean, all of those like machine learning issues will continue to be there, right? So, I mean, like if you have like a very high dimensional embedding for say each one of the nodes, right, which are going to translate into more number of parameters in your downstream model, because the model has to assign parameters to like interpret these different dimensions, right? So now if you don't have too much label data in whatever downstream task you're trying to apply this to, then like, if you have lots of parameters and limited data, then it's going to overfit, right? So
Yes, right. But if we use pre-trained data, which is pre-trained on some bigger knowledge graph like a concept net,
yeah,
and we want to train that pre-trained model on our custom data. But now for custom data, we have a very small knowledge graph, and we have using the same dimension where they used for the concept net. Now to match the dimension, we use the higher dimension. So my question is, does it affect the learning process?
so you will have to see like, in what spaces these different knowledge graphs and their embeddings are, right? Because just because you're matching the dimensions, right, it's
Yeah.
not necessary that they are in the same space, right?
Yes.
So if you're learning something from ConceptNet and something else from your custom domain specific knowledge graph, you also have to find a way to either reconcile or like, put them all through. Maybe you are going to like, concatenate and then pass it through your downstream models wherever you're going to use it. But then it's going to increase the number of parameters even further, because now you're concatenating those two embeddings, right? So you'll have to find a way to maybe reduce dimensions from those so that it's like, more related to the like, which can be handled using the limited amounts of training data that you have for your downstream task.
Okay. And so last question, like
Yeah.
Transy we generally use for the multi-relational knowledge graph, and if we don't have a multi-relation in our knowledge graph, then
Right.
which embedding will be more beneficial?
So there are like, the methods like starting with like node to vec style approaches, and there are like, lots of like other follow-up works on that. So there you can like, utilize, like say someone mentioned about like skipgram type of ideas. So you can do things like, okay, if I have my neighborhood of a given node as the context, so based on those embeddings, how I can like, predict what the embedding of the, say, the centered node that I'm currently focusing on. So you can utilize those kind of ideas. So, I mean, of course, you can use Transy style methods also, but in that case, you're just going to have like one relation. which is going to just be doing the translation part.
Yeah, right. Okay, thank you, sir.
Sure. So Ankush has a question for NEL, WordNet, and all were used for embeddings. If we have a domain-specific KG, then how this job will be done? Do we need to create a dictionary? What job are you talking about, Ankush?
Sir, like the work of clustering and embeddings creation, like the synonym entities and relations were bring closer. So this all
Yeah.
were achieved. We need a reference for that.
Yeah.
But
So
these all are online available or Wikipedia data which are general. But if we have
right.
some domain specific, then how we will do this work?
Yeah, so I mean, like, if you don't have like any side information, then I guess like you're out of luck in terms of utilizing the side information. But then like, the extractions that you are going to do from the KG, I mean, this you can just apply to any domain's data. So it's not like, tied to any schema, and that's kind of like the benefit of open knowledge graph. So you could use this, but the side information could also be useful for like the remaining language phenomenon, even though your domain specific entities may not be well covered, right? So for the domain specific part, then you may just have to rely on whatever extractions you're able to do from the corpus of your domain.
So for OpenKB construction as well, the entity has to be recognized under a specific category like name, organization, place.
No, so these are just all in the noun phrase level, in the surface form, whatever you find them in the corpus, right? Whatever these additional inferences you do, like we are doing here to discover the entities, those are additional layers of work on top of the open knowledge graph. So since you don't have to do all of those like additional inferences just to build, that's what makes open knowledge graphs easier to build or easier to get started, as compared to ontological knowledge graphs where you have to build category and relation specific extractors to do even the first cut extractions.
Yes, sir.
Okay.
Thank you.
So yes, I talked about this, and then graph convolution networks are another more recent ways of learning graphs or doing deep learning over graphs, and you basically you are trying to learn embeddings for these different nodes, and then you can think of as when I'm trying to update the embedding for the center node, I do some sort of weighted aggregation from my neighbors, do some normalization, and pass it through some non-linearity to get the embedding for the center node, right? And then for the center nodes, maybe you have some property that say like, okay, this is a noun phrase or an entity, and I know its type. So based on the embedding that I learn, I make some prediction, and based on the prediction of the loss that I suffer, I do backpropagation to update the parameters, which are these W's and the B's here. So, so we had a tutorial a couple of years back. So if you're interested, you can look at this. And I think there have been subsequent tutorials on this particular topic as well. But when you apply GCNs to multi-relational graphs, then you, and if you say replace each one of those relations as a separate parameter matrices, then you have like a parameter explosion. So we had a method called comp GCN, that basically applies graph convolution networks over knowledge graphs, but in a parameter efficient manner. So in the interest of time, I'll not go into the details of those. But we have also applied these kind of GCN style approaches for doing open knowledge graph embedding, like in the spirit of what I was talking about earlier, but by using deep learning methods now, how we can learn graph level representations and not just like individual nodes. So where some amount of pooling is necessary. And then most of the graphs that we have talked about so far are binary relations graph, right? So where what I mean by that is like, so the relations have two arguments, but then if you want to represent like, real world, say, events and phenomenon, those are not always binary. For example, like say if you have a bomb blast event, right? Then you have like the perpetrator, you have the victim, you have the time, location, what type of material was used. All of those things are related to that same concept. So the binary relation is not sufficient to represent those kind of phenomena. So that's where hyper edges become important, right? So hyper edges are generalizations of these kind of binary graphs, where a single edge is not limited to just touching two nodes, but it can touch more than two nodes, right? So we have also extended these kind of like graph convolution network ideas for hypergraphs, and which are called hyper GCNs, hyper GCN. Okay, so that brings us to the end of part 2. I guess I'll not go into the details of part 3, but I just want to mention about this idea of so the problem of word sense disambiguation, where Pushpak has done so much of seminal work in the area. So there, and maybe you have already covered this in your class before. So if I have the word like tie, tie could mean many different things, right? There are many different senses, where these candidate senses are given upfront. So necktie, it could be tie as an equality in terms of like a context, or connect, severed my ties with that person, right? So multiple senses. So how do we select different sense? So that's where we basically utilize this external knowledge graph, which in this particular case will be a word net, or like a dictionary, which has these definitions of these types of noun phrases. So what we do is that, so we have basically the one is the word net information, which you can think of as a lexical knowledge graph. So for the senses, we basically learn some sort of embeddings by doing some KG embedding of the form that I was talking about before. Then for each one of those senses, we also have a definition that's available as a side information, right? So now by doing some sort of deep learning method, we also get an embedding for this sense, but coming from the definition, right? And we enforce some sort of consistency between the embeddings that we are learning from these definitions and from this external lexical knowledge graph. And by doing all of this, we get the sense embeddings, right? Now, basically, we utilize these sense embeddings to make the prediction for the word sense disambiguation problem in a context-specific manner. So you can think of this as like, for the word sense disambiguation, I have my labels are the senses of the words, the candidate senses. But rather than treating those candidate senses as like discrete labels, we embed them in some space. And in order to learn those embeddings, we utilize a KG embedding method and also these definitions. And a KG in this particular case is a lexical knowledge graph, which is like, say, WordNet, right? So that's kind of like the key idea. And because we have these types of embeddings over the senses, now it allows us to do zero-shot generalization, right? So if you had like a discrete label, for a label that is necessary during test time, but you have not seen during training time, there is nothing you can do about that. But if you are utilizing these kind of embeddings, and that new sense embedding is in the same space as, say, your embeddings of the senses that were used during training time, now you can still hope to do something with that new sense and not go completely blank on that. And we had a bunch of results showing that if you utilize this kind of external knowledge graph, lexical knowledge graph in this particular case, and then use these kind of definitions and put them all together, then you are able to learn better representations, which will allow you to generalize better. We have also done work on doing question answering over these knowledge graphs. So if you have things like who starred in other films made by the director of Titanic, so knowledge graphs are going to be sparse, right? So if you have like a Titanic, and then you have James Cameron. James Cameron also directed this other movie. So if this edge was there, then using this 2-hop, you could have answered this particular question. But now with the missing edge, now you have to use like a longer path to answer the same question. So we have some method which basically handles this kind of sparsity in the knowledge graph to do question answering over them. And that method is called embed KGQA, and there is some benefit compared to other previous methods, especially for doing reasoning over sparse knowledge graphs. And then we have also extended the work to not just restricted to text, but also utilize for other modalities like vision. So in this particular case, if you want to ask the question how many people are there in this image, the standard VQA methods will do a pretty good job saying that, okay, there are 3 people. But if you ask like a person standing to the left or right of just the content of the image itself is not good enough. We also need to know what is the real world identity of these entities. So an external knowledge becomes essential. So now if you have like a knowledge graph where you could link these entities which are present in the image and then do reasoning over them, then maybe you could answer the question, do all of them have the same occupation, right? So okay, this is Elizabeth Warren, Barack Obama, and Richard Cordray. All of them have their occupation to be politicians. So I can say, yes, all of them are politicians. So we have released a data set called KVQA. So this is like knowledge-enabled visual question answering. That has 24,000 plus images, 183,000 plus QA pairs. So excellent source to throw your favorite deep learning methods or the new ones that you're developing, and then work across text, vision, and knowledge graphs together. So in today's talk, I've talked about that knowledge, learning needs context, and knowledge graphs can provide that context. Neural KG embeddings can allow us to go from the symbolic to the continuous space, and incorporation of KG can help improve performance. And then in my group at Google Research, have divided our work in 2 streams. So one is knowledge graphs, in particular around temporal knowledge graphs, and the other one is around multilingual learning, where we are looking at how to advance the state of the art significantly for learning with limited supervision and low resource settings, and we can do better for languages like say Indian languages, where there is a need to provide technologies in local languages which could impact hundreds of millions of users. So anyway, I mean, knowledge graphs are super important, right? And at Google also, they are extensively used all over the place. So if you say do Google search, and you may have seen this panels show up on the right-hand side. That basically is based on a knowledge graph that Google has built and has maintained over the years. So I think knowledge graphs in their own and their relationship with deep learning, especially in low supervision settings, are I think extremely interesting, and hope I provided you some food for thought and some initial pointers in this direction. So I'll stop here. I see that there are a few questions. I'll be happy to address them. But if you have any more questions, please feel free to ask. And I know that we went significantly overboard time, and then we had also the delayed start. So apologies for that. But thanks again for your time, especially on a weekend, for coming and hearing about knowledge graphs and deep learning. So Pushpak, will it be okay to maybe address the questions in the chat? Yeah. Okay.
Yeah, sure.
So Sandeep asks, source of data is important for KGs. How do we ensure that a source is genuine one? We might decide a few trustworthy sources, yet there could be fake information. Yeah, so I mean, Sandeep, that's an excellent question, right? And a very hard one. So in past, we have done some work on determining trustworthiness of sources. And then again, that's also topical, right? Because for some topics, some sources might be more important. So we feel that there is no kind of universal way to determine that, but or like in unsupervised way, it might be hard to do that. But utilizing some signals from users about their trustworthiness, because again, this could be like a personalized decision, right? What you find to be trustworthy, I may find that to be different, and our judgments could vary. So one way to capture that in the knowledge graph could be in the form of source as additional context in the facts. So I mentioned about time. So you could also have source as additional context in the facts, and then let the downstream tasks and users decide how they want to utilize the information from different sources, because there may not be a universal way to decide which one is trustworthy and which one is not. Add on to Swarup asks, add on to Sandeep's question, are there any bias phenomenon in KGs? Yes, I mean, sure, right? So there are going to be biases in terms of like what data you are going to feed into this KG. Then the extraction methods may have their own biases because they may find extraction of certain types of knowledge to be more favorable. For example, we found that on the web, you talk a lot about politicians and sports persons, right? So the knowledge graphs like say NL also have like a disproportionate representation of politicians and sports persons, right? But maybe not so much about like say Indian academics, right? So yeah, so like detecting those kind of biases and how you could mitigate them are all like very important questions to be addressed. For neurosymbolic learning, I have observed that it is mostly about KGE, graph networks, etc., and then using them as part of end NLP application. I'm looking for pointers where both symbolic and subsymbolic learning happens really in joint manner. Maybe not just learning, but also inference. Would you? Yeah. So the coupling constraints and the horn clauses learning type of work that I was talking about earlier. So those you could interleave between the two, right? So where you are learning those constraints and you are utilizing those constraints to learn the embeddings better, and then you are using those embeddings to learn the next version of the knowledge graph, which could allow you to learn better constraints on top. Because if you have like a more densely populated graph, then maybe you could learn these kind of constraints also in a better manner. So KGs generally are created using entities as nouns. That is to answer factoid type questions. Will it be useful to have entities as paragraphs when needed in KG, and if any work is done in the past? So entities as KGs. So how do you plan to use the paragraph, Ankush? I mean, there are efforts to have the knowledge graph where the entities are what we think of as entities, but then also retain the text information with some sort of linking between the entities in the KG and some raw blobs of text on the document side. So that exists, and I guess that's not too far off from your entities as paragraphs, because entities themselves don't have much much significance to them. It's just that how you are representing them in your data structure and how you are processing them. So I don't know whether if you put all of those paragraphs as nodes, then you may lose out from the document structure. So tomorrow you may need to utilize the whole document, and their ordering of those paragraphs may be important. So I think it's a good idea to represent both KG and text together. But what is the right data structure to represent them? Whether we should use graph for everything or something else, I think that's a question. But yeah, but people have looked at And that's a very active area of work as well, of looking both KG and text together. Okay, Vishal asks, I have seen a paper where story generation is carried out by fine-tuning GPT-2 with knowledge graph and then with stories. The authors change the KG into sentence-like structure. Is the essence of the KG lost by doing so? Yeah, so that's a good point. So, I mean, there is a question of like, whether yeah, I mean, you could embed the KG into your large language model by say representing the KG as sentences and then just feeding everything into say one giant black box, and that may work well, but having the graph structure separately also has its benefits, because now, as we were saying, we live in a dynamic world where things become obsolete or the world state changes. Now, if you have to incorporate those changing world state in this kind of like a KG augmented language models, then you have to retrain that model every time the world changes, which is going to be inefficient. So if you're able to factor these things out into a separate external source or memory like knowledge graphs, then that could give you good modularization, good factorization in terms of updating them separately. And then also the benefit of interpretability. So if you're able to ground whatever reasoning or decision making you are doing over the knowledge graph, at least partially, that could give far more insights to the user. So yes, to answer your question, I mean, this is very possible, and this is like a way to incorporate KGs into say a language model. But for the reasons I mentioned just now, maintainability and interpretability at the very least, there are also good reasons to keep them separate from each other. And then then of course integrate them finally, but have their sources and their embeddings separate. Okay, so there is a question from Sapan. Do you have any pointers where other type of knowledge, rules, equations are used to improve an application? I mean, there is lots of work on utilizing constraints. So you can look at Dan Roth's work where he has, I mean, this is from a couple of years back, where he, and I guess mostly non-deep type of methods, but the ideas are still relevant. Of now it is kind of constrained conditional model, CCM, I think he calls it, where they use these kind of constraints during learning. Yeah. And yeah, it's a quite popular way of incorporating side information. And in some of the work that I mentioned, in also NEL utilizes those kind of ways. But the question is kind of whether those are manually specified or automatically learned. So I think that's in both of those two aspects, I think interesting questions are there. Okay, so if there are no more questions, then we can stop here. And again, thank you for your time. Over to you, Pushpak.
Thanks a lot, Partha. Thanks a lot for all your time, question, answer, and all this valuable knowledge that you have imparted in this talk. It will surely help a lot all those students, researchers who are using knowledge graph. We are using them quite a lot in various domains, medical domain, customer support manuals, aviation safety, a number of places.
Right.
So this has really helped a lot. And thank you very much. We have recorded your talk.
Okay.
So I hope that is okay.
Yeah, that's fine.
Yeah.
Okay, great. Thanks a lot, everyone.
Thank you.
And thanks, Pushpak.
We should clap for Partha.
No, that's okay. Your time itself is the most valuable gift. So.